This is problem 15 from chapter 17. In this problem, we want to determine the moment of inertia about an axis perpendicular to the page and passing through the pin at point O. The thin plate has a hole in its center. Its thickness is 50 millimeters, and the material has a density of 50 kilograms per meter cubed. We can use the density and the thickness that they gave us to find the mass that we need. In this problem, we can say the moment of inertia, let's say total, is equal to the moment of inertia for the plate, which is what we would have without the hole, minus the moment of inertia for the hole. So they told us this back here. If you have different parts to your object like we had for the pendulum here, you can add the moment of inertia for the rod and the moment of inertia for the disc. But if you're missing a piece, then you can subtract the missing part, the moment of inertia for the missing part, to get the total moment of inertia. Okay, also we're going to have to use the parallel axis theorem, which was on page 415. So we have the moment of inertia about the mass center given to us, about an axis passing through the mass center given to us on the back cover of the book. And we can add md squared to that to get the moment of inertia which we need, which is going through point O. Okay, so let's turn to the back of the book and see what we have for the moment of inertia for the thin plate. So for the thin plate, for an axis going through the mass center, the moment of inertia is 1/12 times m times a squared plus b squared. And for us, a and b are the same. They're both 1.4. So for the plate, we have 1/12 times the mass of the plate times 2 times 1.4 squared, plus, from the parallel axis theorem, the mass of the plate times d squared. Let me show that to you on the equation sheet. For the parallel axis theorem, it's plus md squared, where d is the distance between the old axis passing through the mass center and the new axis, which is here. So this distance is d, and if we have 1.4 meters there, then this is 0.7, and this is also 0.7. So d squared is 0.7 squared plus 0.7 squared, which is twice 0.7 squared. So this, since this is d squared, that's 2 times 0.7 squared. Okay, so all of this was for the plate. Now we want to subtract the moment of inertia for the hole. So I can treat the hole as a disc, and the moment of inertia for a thin circular disc rotating about an axis going through its mass center, that's 1/2 mr squared. So this is 1/2 times the mass of the hole. The radius of the hole is 150 millimeters, so that's 0.15 squared, plus you have to use the parallel axis theorem here also, so that's plus the mass of the hole. And thankfully, the axis that goes through the mass center of the hole is the same and is in the same place as the axis that goes through the mass center of the plate. So d is the same for both of them. So that's the same d that I had over here. So that's twice 0.7 squared. And this is for the hole. So now all I have to do is find the mass of the plate and the mass of the hole. And I know that the density is equal to the mass over the volume. So the mass is equal to the density times the volume. So the mass of the plate is equal to our density, which is 50 kilograms per meter cubed, times the volume of the plate, which is 1.4 times 1.4. So that's 1.4 squared, times the thickness of the plate, which is 50 millimeters. So that's 0.05. And that gives us, for the mass, 4.9. And the units for that are kilograms. For the mass of the hole, it's the density times the volume of the hole. So because it's a disc, the area for the top of the disc would be pi r squared So that's pi times 0.15 squared. And then for the volume, you have to multiply by the thickness, which is 0.05. And that gives me 0.177 for the mass of the whole. Okay, so now I can put that back in my equation up here. And so I have 1/12 times the mass of the whole, which is 4.9, times 2 times 1.4 squared, plus, did I say the mass of the plate or the mass of the whole? This is the mass of the plate, and that's 4.9 times 2 times 0.7 squared, minus 1/2 times the mass of the whole, times 0.15 squared, minus what I have here, which is the mass of the whole, 0.177 times 2 times 0.7 squared. And so that gives us the total moment of inertia. And for that, you can do the calculation on your own, but you should get 6.23 kilograms times meters squared. And that is our answer for problem 15.